Welcome back to the channel. Today we are diving into the powerful world of AURIX TC275 microcontroller, especially its versatile analog to digital converters or VADC. Whether you are building automotive systems or embedded application, understanding VADC is key. Let's break it. Once again, welcome to the Cocowatt Media. We will cover the following topics. First, we'll understand basics of ADC, then how VADC converter works, on an overview level of the SAR ADC implementation. Further, we'll look into the VADC feature list and different concept in the VADC, how it works. Then jump to the VADC configurations. Finally, we will understand result handling of the VADC converters and safety features. Your vehicle is full of sensors, feeling temperatures, pressure, speed, and many of them are analog. Let's take throttle position sensor. The throttle position sensor tracks how far you press the accelerator. It outputs a varying voltage, usually between 0.5 volts and 4.5 volts, depends on the throttle positions. Temperature sensors like the engine coolant temperature sensor or intake air temperature sensor use thermistors resistors that change the value with temperature. The CAS ECU reads the changing voltage to adjust the fuel injection and cooling. And manifold absolute pressure sensor measures air pressure in the intake manifold to help calculate engine load. It's a crucial for adjusting fuel and timing. And also pressure sensors are everywhere, monitoring oil pressure, brake sensors and fuel pressures. They typically output analog voltage that indicate system health. And even in healthcare, the pressure sensors are key in blood pressure monitoring. They detect the air pressure changes inside the cuff, and this data is converted into your systolic and diagnostic readings. And also in the ECG sensors, which are placed electrodes placed on the skin, measures tiny electrical analog signals generated by heart. So everywhere most of the sensors will give the data in analog, but the microcontroller will not understand directly the analog sensor data. So we need a ADC which converts from analog to digital. Temperature sensors like the engine coolant temperature sensor or intake air temperature sensor use the thermistors. So here what happens is, when temperature is increasing, the resistance get reduced. Now if you connect to some external circuit, so this behavior you can simulate to vary the voltage levels. So now when the temperature is varied, resistance will vary. With respect to that, the voltage levels also will get vary. Our microcontroller is able to read the voltage variation. With that, we'll calculate the temperature value in our microcontroller. Now let's talk about how an analog sensor connect and interact with a microcontroller using a 12-bit ADC as an example. Imagine you want to measure a system supply voltage. We will design a simple voltage divider circuit that outputs 3.3 volts when the supply voltage is at its maximum, say 24 volts, and 0 when the supply is 0 volt. The output of this voltage divider will then be connected to the ADC input channel on the microcontroller. Here is an important concept to understand. The ADC works between two reference points, positive V reference and negative V reference. Positive V reference is the maximum voltage the ADC can read, usually equal to the microcontroller supply voltage like 3.3 or 5 volts. Negative V reference is the minimum voltage which is typically ground. For a 12-bit ADC, when the input voltage is 0, the ADC output will be 0. When the input voltage is 3.3 volts, the ADC output will be 4096. This is because a 12-bit ADC has 2 to the power of 12 or 4096 descriptive steps. So if you wanted to calculate the ADC value, here is the formula. ADC value is equal to input voltage into maximum descriptive steps, that is 4096 divided by V reference. Now assume the input voltage is 1.65 voltage. Then substitute this value into the formula. You will get 4028 has a ADC value. That's how an analog sensor voltage is translated into a digital value that the microcontroller can understand. The TC275 microcontroller includes a set of analog input channels connected to a group of analog to digital converters or ADCs that use the successive approximation registers method to convert analog voltage into digital values. Each ADC within this cluster works independently with its own control registers and trigger sources. This means multiple conversions can happen in parallel without interfering with each other. The digital output from each channel can be stored in its own dedicated result registers or in a shared group result register, depends on how you configure it. There also a background request source that handles any unused analog input channel. Those conversions run with lower priority, making the background request source act like an extra low priority converters running in parallel. VADC uses individual successive approximation registers or SAR converters, each with its own dedicated sample and hold unit for capturing signal accurately. If you would like to learn more about how SAR ADC works, drop a comments below. I'll be happy to create a separate video explaining in details. Let's take a look at the key features of ADC cluster inside the TC275 microcontroller, designed specially for high performance automotive applications. The ADC cluster operates with a nominal analog supply voltage of 5 volts, but it can also run at 3.3 volts with slightly reduced performance. It can handle input voltage ranging from 0 volts up to the full analog supply voltage. For each channel, you can select between a standard reference voltage or an alternative reference via channel 0. This supports ratiometric measurements and allows for handling different signal level. The cluster includes up to 8 independent converters, each capable of handling up to 8 analog input channels. It also supports external analog multiplexer control, letting you adjust sample times and scan setting to match your sensor needs. You can fine-tune conversion speed and sample time based on the sensor characteristic and reference quality. Some conversions can complete in under 1 microsecond, depends on the sample time and result resolution. The ADC cluster offers flexible triggering and sequence options. You can program cluster conversion sequence, set up auto scan operation either per converter or across all converters, trigger conversion manually through timer or via external events. It even supports cancel inject restart modes, which help prioritize urgent channel and reduce conversion delay. And for result process, you get selectable results width of 8, 10 or 12 bits. Fast comparison mode for quick threshold checking, independent result registers for each channel, configurable limit checking and automatic filtering using FIR or IR technique. On the safety side, the ADC includes configurable register protection for critical applications, broken wire detection with programmable default response level, a multiplexer test mode to ensure signal quality, path integrity. Finally, the ADC cluster fully support and suspect and power saving modes, ideally for today's energy efficient automotive design. All the analog to digital converters receives a global clock signals known as FVADC. From this input, two separate clock signals are generated and shared across all converters. A global configuration register sets the common clock basis for the entire converter cluster. This setup ensures predictable and synchronized behavior, especially when multiple converters need to operate in parallel. The key clock signal for the analog converters is called FADCI. It directly affects the performance of converters, and it's important to select it carefully. The analog converter inside the ADC is the core block responsible for converting the selected input voltage into a digital value. While operating, it continuously draws current, but to save power, it can be turned off between conversions. After a system reset, the analog converter are switched off by default. You must be enabled them before starting any ADC operation. To ensure accurate conversion, the analog converter can be calibrated to automatically compensate for variation in process, temperature and supply voltage. If ANONS is 1 then it is a normal operation. The converter is active and start conversion immediately. No wake up time is needed. When ANONS is 10 or 01, these bits are reserved for the future usage. And when it is 00, it means the converter is off. The converter remains powered down. Digital control logic is reset to its initial state. If a conversion arbitration is in progress, it will finish the current round and then stop. Before launching a conversion, make sure to set the conversion to active mode. Switching the analog block back on introduced a wake up time. So for time critical application, the configuration must be chosen carefully. Managing the conversion operating modes smartly help you to balance performance and energy savings, especially in automotive system where every microamps counts. ADC conversion can be triggered through software and also from external trigger, maybe like hardware signals. In a queued request source, you can create short conversion sequence up to 8 channels with full flexibility in the order you choose. Unlike a scan request source, which follows a fixed conversion order, the queued request lets you set any sequence you want. These channels are stored in a queue buffer organized with the simple FIFO mechanism. The channels to be converted are loaded into the queue, and queue stage 0 always holds the next channel to be converted. A conversion result is only sent to the arbiter when there is a valid channel ready in stage 0. Now, if a conversion gets interrupted, say a higher priority request comes in, the system automatically saves the aborted conversion into a backup stage. This way, no conversion is lost. Instead, the aborted conversion gets another chance in the next arbitration cycle even before stage 0 is processed. The trigger and gating unit plays a key role here. It listens to selected external signals. For example, a timer can send out a request to align conversion with PWM event. Trigger event can come from either software component or hardware signal. When a trigger event happens, it kicks off a queue conversion sequence and the QSRX.EV flag gets set. This flag clears once the corresponding conversion starts or when you manually clear it by setting the QMRX.CEV bit. The VADC provides two types of channel scan sources: group scan source, background scan source. Both sources operate in a same way and provide the same register interface. The background source provides more request pending bits because it can request all. Group scan source can request all channel of the corresponding group. The scan request source of a group X can schedule a linear sequence of conversion for the associated converters. Each channel of group X can be included or excluded from a sequence. A sequence can be repeated automatically. The conversion sequence can be started either via software or via a selectable trigger signals from on-chip and external sources. The ADC will convert all the selected channels from the channel with highest number to the lowest one. Background scan source can request all channel of all group. The ADC will convert all the selected channels from the channel with highest number to the lowest one. These channels taking part in background scan can be on all the ADC module. Request source arbiter regularly polls the request sources one after the other for pending conversion request. Each request source is assigned to a certain time slot within an arbitrary round called arbitration slot. Arbitration slot 0 is 8 stage queued group sources, 8 stage sequence in arbitrary order. Arbitrary slot 1, n scan group source with SAR group input channels. Arbitrary slot 2, virtual background scan source sequence in defined order. Last arbitration slot, synchronization source synchronized conversion request from another ADC kernel. Duration of an arbitration slot is configurable and duration of arbitration round therefore is 4 into T slot. Analog input channel configuration. Several parameters can be configured that controls the conversion of each analog input channel. Simple time for this channel and the data width of the result are defined via input classes. Then select the reference voltage, standard reference or CH0. Then alias features, conversion request for channel 0 or channel 1 can be redirected to other channels. Result value can be stored in one of 16 local registers or in a common registers. Result locations can be selected channel specific or source specific. And finally, select the result position. Results value can be stored left aligned or right aligned. Channel event handling. Channel event can be generated whenever a new result value becomes available. Channel event generation can be restricted to values that lie inside or outside a user configuration band. Each result register has an individual data valid flag associated with it. This flag indicates when new valid data has been stored in the corresponding result registers and can be read out. Result registers can be read via two different views, application view and debug view. The data can be stored. The position of a conversion result value within the selected result registers depends on three configurations. Selected result width 12 or 10 or 8 bits, selected result positions left or right aligned, and selected data accumulation mode. Additional test structures can be activated to test the signal path from the sensor to the input pin and the internal signal path from the input pin through the multiplexer to the converter. These test structures apply additional loads to the signal path. Pull down diagnostic. One single input channel provides a further strong pull down that can be activated to verify the external connection to a sensor. Multiplexer diagnostic. To test the proper operation of the internal analog input multiplexer, additional test signal can be connected. In combination with a known external input signal, this test functions shows if the multiplexer connects any pin to the converter input and if this is the correct pin. Converter diagnostic. To test the proper operation of the converter itself, several signals can be connected to the converter input. Test signal can be connected to the converter's input either instead of the standard input signal or in parallel to the standard input signal. Thank you for watching. In the next video, we will dive into the VADC configuration registers and walk through a demo. Don't forget to like, share and subscribe so you won't miss it.